practice with scatter plots and linear models. So first we're going to interpret the slope of this model. Well, the slope you can see is positive, and it's 1.0472 over 1. Now, what is represented in the numerator? Well, it's the y value, so we're talking pounds of meat consumption per capita. And the denominator would be years since 1905. Now, when we go for an interpretation, right, there was a 1.0472 pound increase in meat consumption per capita in years after 1905. Right, that's what our model is showing us. You can see there has been a little bit of a decrease in actual poundage eaten per capita in the recent years. But anyway, there is your slope business. Use the linear model to estimate the meat consumption for 2010. Okay, so they give us, here's the actual, but we want to use this to find the estimate. So X would be 2010. So Y equals 1.0472 times 2010 minus 1916.4. And when I do that, I first multiply and then I subtract. I would get a value of 188.5. I went ahead and rounded. 188.5 pounds is the estimate, which would be up here. Well, maybe not that far up there. It's hard to do this on here. 188 would be right, right there. How does this model estimate the actual? The estimate is higher than the actual. Right? Because the actual is this dot down here. The actual is 172.9. It's like 13 pounds higher. That's a lot of meat. Calculate and interpret the linear correlation coefficient. Well, R squared is 0.8923. Square root both sides, and R is 0.9446. Positive because my slope is positive. Interpret that. There's a positive, strong, linear correlation between pounds of meat consumed per capita and years since 1905. But you can still see the actual data varies, right? You have varying data, but the model shows that there is a correlation between the years and the pounds of meat consumed. Would it be reasonable to go out to 2025 in this? So that would be like out here. No. No, it's outside the scope. Outside the scope of the model. Let's go to a different graph. Let's use the linear model, right? The linear model is the actual equation that they give you to predict the life expectancy for a country with the GDP per capita of 100,000. You will see GDP per capita here is the X value. So Y equals 0.0002. I want to plug in 100,000. And then I'm going to add 66.819. So first I multiply, then I add, and I end up with, where's my answer? 86.819. So life expectancy, if you have a GDP per capita of 100,000, you should have a life expectancy of approximately 86. So do any countries have that life expectancy and GDP? Well, the GDP here, here's the 100,000. 86 would be like right here. No, there are no, Luxembourg, these are the dots that are closest, but nobody has that. No, right? That's what's expected, but nobody is there. Calculate and interpret the linear correlation coefficient. So R squared is 0.3439. We square root both sides. It's positive, so R is going to be a positive 0.5864. I would say there is a weak positive linear correlation between life expectancy and GDP per capita. And I say it's weak because 0.58, we're in the 0.5s, close to 0.6. We're just not real strong. It's to be strong, you've got to be up in the 0.8s, 0.9s. That gives you kind of a strong correlation. But here down in the 0.5s, now that's weak. That's weak. And there's your practice on scatter plots and linear models.